Okay, so now we're moving into section 6.3. In 6.3, we're going to be a little more general in regards to projections than we were in section 6.2. And we start off with, well, the big theorem is what's called the orthogonal decomposition theorem. But you've already seen this with the last example, but this is more general. Here, what we're going to do is we're going to let W be a subspace of R. And every vector Y in R can be written uniquely as the sum of two vectors, a vector Y hat and a vector Z. Now Y hat, okay, is going to be in subspace W, and vector Z is going to be in W perp, which is perpendicular subspace W. So you saw actually that from section 6.1 you were introduced to this W perp, or W perpendicular space. W perp consists of this. I'd like to kind of highlight it a little more, but it's fine. This W perp space consists of all vectors that are orthogonal to the vectors in subspace W. So they are orthogonal subspaces. Orthogonal subspaces. And what we're doing is we're taking a vector Y and we're expressing it as the sum of two vectors, each in like both vectors are in subspaces, but the subspaces are orthogonal to each other. And you know that if you have any orthogonal basis of W, the vector Y hat, which is your projection vector it's a projection of Y onto the subspace W, that can be written this way. Okay, this is that what we saw in the geometric interpretation of Theorem 5. Only now, let me show you what that geometric interpretation is. Okay, let me show you. So let me go here down a little bit there's a picture. Yeah. Geometric interpretation of an orthogonal projection. Now what we're doing is we're not like the interpretation you saw from section 6.2 was when the vector Y and the orthogonal vectors U1 and U2 were in a two-dimensional space. Now what we're doing is we have an n-dimensional space, but for the picture here, they're showing a three-dimensional space. Okay, but so they have this vector Y. Okay, the vector Y is right here. Okay, I can't really. I mean, you see here a vector Y, which is this blue dot here at the top. And in the x1, x2 plane, you have orthogonal vectors u1 and u2. And the vector Y can be thought of as projections, the sum of two projections. One is the projection of the vector Y onto the subspace spanned by u1, and the other is the projection of the vector Y onto the subspace spanned by u2. So the vector Y is the sum of those two projections, but you're now looking at it in terms of a higher dimensional space. And the orthogonal projections, the orthogonal projection of Y is the sum of its projections onto one-dimensional subspaces that are mutually orthogonal. And that's what they're demonstrating here. Okay, that's really what they're demonstrating there. So I think I think it's best to get right to some examples. Okay, so, but are there any questions in regards to the picture in the figure 3? Okay, Matthew's good. Thank you, Matthew. Kevin's good. Christy's good. Good. Okay. All right. Well, then let me bring up our new example here, or new examples. Okay. So we're going to do 2 examples from section 6.3. Let me give you a moment to copy this example down. Okay, so what we want to do is we want to find the closest point to the vector y in the subspace. Wait, hold on. Yeah, that's fine. All right, we want to find the closest point to the vector y in the subspace spanned by v1 and v2. And then we want to find the distance from y to the subspace spanned by v1 and v2. Okay, that's what we want to do. So, all right, it'll be helpful to draw a little picture here. So what I do, and you know, this of course, where do these vectors live? Where do these vectors live? In what space do they live? They live in R4. That's right, Solomon. So you know, I can't draw a 4-dimensional space, but I can conceptually draw a picture that'll help me get a feel for this problem. So what I do is I say, okay, here's a picture of a space W and two vectors, V1 and V2. And by the way, the vectors V1 and V2 in this problem, what do you notice about vectors V1 and V2? Those vectors are what? Those vectors are they're linearly independent. That's right, Solomon. Anything else? They live in R4. Try to give you a little hint here. Yeah, they're orthogonal. Robin, how do you know those two vectors are orthogonal? How can you confirm that? Confirm that. Good. The dot product of V1 and V2 equals 0. That's right. That's right. And so in my little picture here, I've just drawn two vectors, V1 and V2. They live in a they live in space W. W is the span of V1 and V2. The dimension of W is 2. It's a two-dimensional subspace of R4. Okay, and this vector Y also, I want to be, yeah, this vector Y lives in R4, but it doesn't live in the, it doesn't live in the span of V1 and V2. Okay, it doesn't live in the, if you were to try to write Y as a linear combination of V1 and V2, you know, Y equals C times V1 plus C times V2, that won't happen. What would happen if you tried to write the vector Y? What if you tried to write the vector Y as C1 times V1 plus C2 times V2? Okay, now it's not equal to that, clearly, based on the diagram. But if you were to try to write a vector equation, vector Y equals C1 times V2 plus C2 times V2, turn the vector equation into a system of equations, solve the augmented matrix, what would happen? What would happen? Could you solve for C1 and C2? I mean, geometrically, you cannot, right? Because the vector Y here, there's no way it's a linear combination of the vectors V1 and V2. And that means if you tried to solve for C1 and C2, you would end up getting what kind of system? What kind of system would result? Good, Binyam, an inconsistent system. Okay, Binyam, by the way, don't go away. There's something I need to mention to you. Nothing bad, but don't go away. Okay, after the lecture's done. Okay. All right. Thank you. Thank you. Okay. So clearly, then we want to find the closest point to the closest point in the space W, which is the span of V1 and V2, those vectors, those orthogonal vectors. We want to find the closest point in that subspace W to the vector Y. Well, the closest point would be found by dropping a line segment down into the subspace W from the vector Y. And what you're going to see then is that the closest point is right here, right there. But that point that point, right, is the projection of the vector y onto the subspace W. So the vector y hat is the closest point. The projection of the vector y onto subspace W is the closest point in space W, subspace W, to y. Okay. One moment here. Hold on, question. So is this the derivation from a distance from a point to a plane? Well, you know, I've not actually looked at that formula in a while, Noah, but there would have to be agreement. What we're doing here, I mean, the answer, let me just see, hold on. Let me just see here. I have my Calculus 3 book right here. Calculus 3, one moment. Calculus 3, one moment. I'm just looking here. The formula should agree. The formula should agree, Noah. They should agree. They have the formula in the book, in the Calculus 3 book, the Math 280 book, looks a little different, but ultimately there should be agreement. Okay, and all right, so good question, good question. So what I do is, all right, I compute the projection of the vector y onto subspace W, that's called y hat, and I compute it, and I do the math here, I'm doing the math, okay, just to show you Dr. Duty can do the math. And so y hat is going to equal, it's going to equal 6/12 times vector v1 plus 6/4 times the vector v2. Okay, give you a moment to copy that down. Okay, and so now let's go to the next page. Here we actually compute then y hat, we work it out, and y hat is going to equal 3, -1, 1, -1. That's going to be what y hat equals. And so that's your projection of the vector y onto the subspace W. And the distance, okay, the distance from the vector y to the subspace spanned by V1 and V2, well, first of all, you got to figure out the difference between the vectors y and y hat. This is what the book often calls the vector z in pictures. Okay, are there any questions on that? I want to make sure I'm not going too fast. Okay. Okay, so what do I have to do then to get the distance? Okay, I have this vector, the vector z. Okay, I have this vector z, and incidentally, let me just show you on the picture here. I mean, this here is the z vector, right? This vector right here. I knew I should have used the that's your z vector, right? Okay. And to find the distance of that z vector, you just take the norm of that vector, and you'll get 2 times the square root of 6. It's absolutely amazing. I mean, Calculus 3, we love Calculus 3, and we see these ideas, some of them in Calculus 3. But Calculus 3, you're working in 3-dimensional space. Linear algebra concepts are generalized to n-dimensional space. I mean, we're working in 4-dimensional space here. Okay, hold on. Okay. Now I'm going to do one more example. I am going to have to do one more example, so I might run a little bit over, but it won't be too much over. Okay, so if you can, it'll be in the recording, but Solomon, Matthew, let me know when you're good with page 3 here, and then I'll go to page 4. Solomon's good, okay. Matthew, how are you? Okay. Everybody else good? All right. Here's page 4 then. So these examples are designed to help you with the section 6.3 homework. You're going to have homework due on Thursday for 6.3, for 6.2 and 6.3. And you really have to make your best effort to work on that homework. Even if you can't get it all done, you want to try to get some of it done, because it'll help you understand then what we'll cover on Thursday. All right, are there any questions? I think people are doing a overall better job on the homework. Some people have, their homework scores are improving. Okay. These stand for the norm of a vector. When you have the double bars, you're finding the length of the vector, the norm of the vector. The vector is y minus y hat. That's one vector, right? So you're finding the length or norm of that vector. So that's notation. That's norm notation. Okay, all right. Let's proceed on. Let's proceed on and do another example here. Okay, let me give you a moment to copy this example down. Okay, so in this problem, again, we're dealing in R4. We have 4 orthogonal vectors, okay, that form an orthogonal basis for R4. So U1, U2, U3, and U4, you can confirm that those vectors form an orthogonal basis for R4. And we have a vector x in R4, and we want to write the vector x as the sum of 2 vectors. One vector that's in the span of U1, U2, and U3, the first 3 vectors, and one that's in the span of U4. Okay, so we're decomposing the vector x into the sum of two vectors. Okay. All right, so what is helpful to me? Okay, all right. Well, Matthew, I have to go to the next page. Oh, I see what you're saying. You're still copying. Okay, no problem. Let me know when you're ready. Let me know when you're ready. Again, you know, if I were in the classroom, I would be able to, you know, see you all copying and all that. All right, no problem. That's, I want you to let me know. I want to thank you. All right, so, okay, so here's what I do. Okay, here's what I do. So we know that we have an orthogonal basis for R4. W is the span of U1, U2, and U3, and W perp, that stands for W perpendicular, that's the space perpendicular to W, that's the span of U4. The dimension of W is 3, the dimension of W perp is 1. I'm just writing down some facts to help me feel comfortable, and hopefully you'll feel comfortable. And then I draw a little picture here where I have two subspaces. So here's subspace W. I drew it as a plane, but just think of it as a subspace. And then everything else is W perp. The union of W and W perpendicular, W perp, is equal to R4. Okay. And what we want to do is we want to write the vector x as the projection of the vector x onto the space W, which is the span of U1, U2, and U3, plus the projection of the vector x onto the span of W perp. Well, I want to be careful. I want to write the vector x as the projection of x onto the subspace W, which is the span of U1, U2, and U3, plus the projection of x onto the subspace W perp, which is the span of U4. Okay, that's what we want to do. Now, the homework, they might have it switched. You know, they might call Doug. Well, I mean, this is fine. Okay, this is fine. Okay, let me give you a moment to copy the picture down. Okay, so now what I'm going to do is I'm going to find the projection of the vector x onto the W perp space. Okay, that is just going to be equal to the coefficient defined by x dot u4 over u4 dot u4 times the vector u4. Okay, and this here is just you can ignore that stuff there. That just shouldn't be there. Okay. So I compute it out, and I will get 2 times U4. 2 times U4. Now keep in mind, class, that if I were to compute, well, no. I could have also computed the projection of X onto the subspace W. But I'm going to instead compute the projection of X onto the W perp subspace. All right, and we want to find out what that vector is, and you'll see why I'm doing this. But I'd like to move to the next page when you're ready. Okay, I'm getting some audibles here. Okay, so what is 2 times U4? 2 times U4 will equal 10, -6, -2, and 2. And that will be a vector in the span of the vector U4, because W perp is the subspace defined by the span of the vector U4. Okay, so now I need to get the other, okay, Masha, thank you. So now we got to get the projection of the vector X onto W. So all I need to do is take the difference between X and the projection of X onto W perp. So it's an easy way to find the projection of X onto W. It's an easy way. Rather than adding the sum of 3 vectors, which is what I would have to do to find the projection of X onto W, by virtue of the fact that X is the sum of the projections, I can find this projection here, the first projection, just by taking the difference of X and the projection onto W perp. Okay, and that made life easy. How many think that's pretty cool? Thank you, a lot of you. Yeah, less work. That's right, Matthew. Solomon likes it, Sega likes it, Robin likes it. Many of you. Excellent, excellent. James, Steve Hart, Kevin, Hugh. I like to try to mention all names. It's sometimes hard to do. But, you know, this is the kind of thinking where if you just use the geometry, If you just work with the geometry, which is why I tend to draw, that's right, Solomon, it's simpler. I tend to draw a picture when I do these problems to kind of get my mind thinking conceptually about what's going on. I tend to like to draw a little picture to help me, you know, just feel comfortable. All right, so are there any questions on this particular example? And I appreciate your staying a few extra minutes. I'm going to make one more comment before you go, but are there any questions? May I? All right, I'll stop the recording.